Have you ever noticed the white powdery substance used in cement and in soil treatment? That's calcium oxide, also called quicklime. But how is it formed? Let's explore the atomic level process that makes this useful compound. Calcium oxide is an ionic compound. It forms through the transfer of electrons, not sharing but a full handover, between a metal, calcium, and a non-metal oxygen. The metallic calcium donates its extra electrons while oxygen accepts them, and both atoms become stable ions. These oppositely charged ions, calcium 2 plus and oxide 2 minus, attract each other strongly, binding together as calcium oxide. This is the beauty of electrovalent bonding. Now, let's zoom into the atomic structure. Calcium, with atomic number 20, has an electron configuration of 2, 8, 8, 2, 2 electrons in its outermost shell. Oxygen, with atomic number 8, has the configuration 2, 6, meaning it needs 2 electrons to reach the noble gas configuration. When calcium loses its 2 valence electrons, it attains the stable configuration of argon, which is 2, 8, 8. On the other side, oxygen gains those 2 electrons to achieve the configuration of neon, that's 2, 8. This transformation is driven by nature's quest for stability, atoms moving toward noble gas configurations. Here's where redox chemistry comes in. Yes, that same duo we see in rusting and batteries. In this reaction, calcium undergoes oxidation. It loses 2 electrons. Say it with me. Ca gives Ca² 2 electrons. Oxygen, meanwhile, undergoes reduction by gaining those electrons. O plus 2 electrons gives O2 minus. So we have a redox process. Calcium is oxidized, oxygen is reduced. This electron transfer leads directly to ion formation, setting the stage for ionic bonding. Let's now represent this using Lewis electron dot structures. Before bonding, calcium is shown with 2 dots, representing its valence electrons. Oxygen has 6 valence electrons around it. When bonding occurs, calcium gives away both dots to oxygen. After the transfer, calcium becomes Ca²+, no dots, just a charge. Oxygen becomes O2-, now surrounded by a full octet. This transfer is not about sharing, it's about one atom giving and the other taking, just like a donation. And visually, it's represented as Ca with a positive charge plus O with 8 electrons and a double negative charge, forming calcium oxide. You can see this in the electron dot diagram on the screen. Let's take a step deeper into orbital shells. In the atomic orbit structure, calcium has 4 shells with 2 electrons in its outermost. Oxygen has 2 shells and lacks 2 electrons to complete its octet. After bonding, calcium's outermost electrons are gone, making it stable like argon. Oxygen gains 2 electrons, completing its shell-like neon. This is visually clear when we look at the orbital diagram. The atoms transform into ions, Ca2+ and O2-, both with full outer shells. This transition from unstable atoms to stable ions is what drives ionic bonding. Now that we've formed Ka2+ and O2-, what holds them together? It's the powerful electrostatic force, opposite charges attracting. This force forms the ionic bond. Think of it like the pull between 2 magnets, one positive and one negative. In solid-state calcium oxide, these ions arrange in a crystal lattice, repeating units of calcium and oxygen ions tightly packed together. This structure gives ionic compounds like CaO their high melting points and solid form. It's not a loose connection, it's a firm, structured bond driven by charge. So, to wrap it up, calcium oxide forms when calcium donates 2 electrons and becomes Ca2+, while oxygen gains 2 electrons to become O2-. These ions attract each other and form a strong electrovalent bond. Electron transfer, redox reactions, stable configurations, all in one elegant process. And remember, the CaO we've been talking about isn't just theoretical. It's used in cement manufacturing, steel purification, and even in treating acidic soils in agriculture. Chemistry like this truly powers the world around us. I hope this session helped you visualize how atoms transform and combine to form the materials we use every day. Catch you in the next lesson with more chemical insights from the invisible world of atoms and ions. In the next video, we'll explore the structure of another electrovalent compound, magnesium chloride. See you there.